This lecture introduces hypothesis testing and discusses many related concepts. In many applications, we need to make decisions about the value of parameters. For example, I give you a coin and expect you to tell me whether this coin is a balanced coin or not. Recall that a balanced coin means that the probability of heads is 0.5. In terms of statistics, I just want you to decide whether the probability of heads is 0.5. You can find many other examples. For example, decide whether the mean weight of all bags of pretzels equals the advertised weight of 454 grams. Decide whether the mean age of all cars in use has increased from the year 2000 mean of 9 years. In all these examples, we need to make a judgment about a parameter. A hypothesis is a statement that something is true. For example, you may claim that the mean weight of all bags of pretzels does not equal to the advertised weight of 454 grams. This is a hypothesis. It can be correct, and it is also possible that it is not correct. In statistics, we distinguish two types of hypotheses. The first one is called the non-hypothesis. It is a hypothesis to be tested. We use symbol H0 to denote it. It usually contains words such as equal, not, no effect, not exist. The next one is called the alternative hypothesis. It is a hypothesis to be considered as an alternative to the non-hypothesis. We use symbol HA to denote it. It usually contains words such as not equal, larger, smaller, exist. The non-hypothesis and alternative hypothesis are complement to each other. We need to make a choice between them. For example, for the weight of pretzels, the non-hypothesis can be that the mean weight of bags of pretzels equals to 454 grams. The alternative hypothesis is that the mean weight of bags of pretzels does not equal to 454 grams. You can see, either the non or alternative hypothesis must be true. In practice, we will take a sample and make a choice between them based on the sample. The problem in a hypothesis test is to decide whether the non-hypothesis should be rejected in favor of the alternative hypothesis. Right now, suppose that we are interested in the parameter mean, denoted by mu. Let mu0 be a known constant. The non-hypothesis is usually mu equals mu0. For example, in the example of pretzels, we are interested in the mean weight of bags of pretzels. Here, mu0 is 454 grams. The non-hypothesis is mu equals 454 grams. The alternative hypothesis can be one of the three cases. It can be mu not equal to mu0, mu less than mu0, or mu larger than mu0. These three cases are referred to as two-tailed test, left-tailed test, and right-tailed test, respectively. The last two are also referred to as one-tailed tests. Sometimes instead of tail, we use the term side. We can call them two-sided test, left-sided test, right-sided test, and one-sided test. To solve the problem of hypothesis testing, the first step is to correctly identify non- and alternative hypotheses. Notice that the non-hypothesis is always mu equals mu0. The alternative hypothesis can be different according to what we want to do in practice. Let's check one example. A snack food company produces a 454-gram bags of pretzels. The quality assurance department performs a hypothesis test to decide whether the packaging machine is working properly. That is to decide whether the mean net weight of all bags packaged is 454 grams. The null hypothesis is always using the equal sign. Why is the alternative hypothesis not equal to 454? In this problem, if the packaging machine is not working properly, the weight of bags may be smaller than 454 grams or larger than 454 grams. Either case may happen. Therefore, we choose the two-tailed alternative hypothesis in this problem. A half century ago, the average US woman in her 20s was 62.6 inches tall. We want to perform a hypothesis test to decide whether today's women in their 20s are on average taller than such women were a half century ago. First, the null hypothesis always uses the equality sign. So H none is mu equals 62.6. In this problem, the question of interest is whether today's women are taller. Pay attention to the word taller. It indicates larger. Therefore, the alternative hypothesis is mu larger than 62.6. Why not use a two-tailed test? In this case, we are confident that there is no way that today's women will be shorter than a half century ago. Therefore, we use right-tailed test. The recommended adequate intake of calcium for adults is 1000 milligrams per day. We want to perform a hypothesis test to decide whether the average adult with an income below the poverty level gets less than the RAI of 1000 milligrams. The null hypothesis always uses the equality sign, so H none is mu equals 1000. The question of interest is whether the mean RAI of adults below the poverty level is less than 1000. We are pretty sure that the mean RAI of adults below the poverty level will not be larger than 1000. Therefore, we use a left-tailed test. Let's summarize the three examples. The null hypothesis always uses the equality sign. For the alternative hypothesis, it depends on our knowledge on the application. If both a larger or smaller value may happen, we use two-sided test. If only either larger or smaller value may happen, we use one-tailed test. It is important to choose the correct alternative hypothesis because it will affect the conclusion of a hypothesis testing problem. The basic logic of a hypothesis test is as follows. We take a random sample from the population. If the sample data are consistent with the null hypothesis, we do not reject the null hypothesis. If the sample data are inconsistent with the null hypothesis and supportive of the alternative hypothesis, reject the null hypothesis in favor of the alternative hypothesis. Notice that to report the result of a hypothesis test, there are only two possible results, namely reject the null hypothesis or do not reject the null hypothesis. Sometimes you may hear others saying accepting the null hypothesis. Strictly speaking, it is not correct. Our default choice is the null hypothesis. If there is strong evidence against it, we will change our mind and reject the null hypothesis. Otherwise, we stay with the null hypothesis. In this sense, we can only say do not reject the null hypothesis. When we perform a hypothesis test, we may make mistakes. There are two different types of errors, namely type 1 error and type 2 error. Look at the table below. For H none, it can be true or false. For the decision, we may reject H none or do not reject H none. 2 by 2, there are 4 possible scenarios. If H none is true and we do not reject H none, it is a correct decision. If H none is true and we reject H none, we make an error. It is called the type 1 error. If the null hypothesis is false and we reject H none, it is a correct decision. If the null hypothesis is false and we do not reject H none, we make an error, which is called a type 2 error. As a summary, a type 1 error means rejecting the null hypothesis when it is in fact true. It is just like telling the old man that he is pregnant. Notice that the null hypothesis is not pregnant, and the alternative hypothesis is pregnant. A type 2 error means not rejecting the null hypothesis when it is in fact false. It is like telling the pregnant woman that she is not pregnant. Let's check another example. A person wants to know whether he has cancer or not. In this hypothesis testing problem, H none is not cancer, and the alternative hypothesis is having cancer. Recall that H none always contains words such as not exist. In this example, if you tell a healthy person that he has cancer, you make a type 1 error. If you tell a cancer patient that he does not have cancer, you make a type 2 error. In the pretzel packaging example, the null hypothesis is that the mean weight of bags is 454 grams, and the alternative hypothesis is the mean weight of bags is not 454 grams. A type 1 error occurs if the packaging machine is working properly, but we conclude that it is not. In another word, mu equals 454 grams, but we claim that mu is not equal 454. If the packaging machine is not working properly, but we claim that it is working properly, we make a type 2 error. In this case, mu is not 454, but we claim mu equals 454 by mistake. This flow chart helps us decide whether it is a type 1 error or type 2 error. First, we need to check whether H none is true or not. If it is true, we need to continue to check whether H none is rejected or not. If H none is rejected, we make a type 1 error. If H none is not true and H none is not rejected, we make a type 2 error. This is another flow chart to decide whether it is a type 1 or type 2 error. It starts with whether H none is rejected. You can use this flow chart to check whether we make a type 1 or type 2 error. Which flow chart to use, this one or the previous one, depends on which one is more convenient. When dealing with a hypothesis testing problem, the probability of making a type 1 error is called the significance level. Usually, we use alpha to denote it. The probability of making a type 2 error is denoted by beta. For a fixed sample size, the smaller we specify the significance level alpha, the larger will be the probability beta of not rejecting a false null hypothesis. It is impossible to make alpha and beta smaller at the same time. Therefore, in practice, we will fix one. Usually, we choose alpha equals 0.05. Occasionally, you may see examples of alpha equals 0.1 or 0.01. If the null hypothesis is rejected, we conclude that the data provide sufficient evidence to support the alternative hypothesis. We can say that the test results are statistically significant at the alpha level. If the null hypothesis is not rejected, we conclude that the data do not provide sufficient evidence to support the alternative hypothesis. We may say that the test results are not statistically significant at the alpha level. In this lecture, we only introduce some basic concepts regarding hypothesis testing. We will discuss how to do in later sections.